I just mute myself.
Yeah, now it's okay.
Oh yeah. Let's start from over again. Thank you. Thanks for the invitation. I'm a PhD student at the University of Exeter in the UK. My research focuses on the question, is deep learning secure for robots? So I deal with hardware, embedded systems, and robots. I'm going to give a brief introduction to embedded systems. If you are not familiar with hardware, don't worry. I will introduce what is embedded programming as well. Let's get started. So what is embedded programming? Maybe you are familiar with web development that designs websites, or you have heard of app development that designs applications such as Microsoft Teams, Microsoft PowerPoint, just to name a few. Or you may have heard of operating system development that designs operating systems such as Windows, Mac OS, Android, and Linux. But what is embedded programming? Well, it's not so intuitive from its name, right? For embedded programming, actually we program hardware. So as you can see here, we program microcontrollers to interface with sensors. Well, I guess it's more intuitive to show you some demo applications. So this is what it looks like to program hardware. We can program a robot that rides a bicycle, and we can program a manipulator to give us a haircut. Embedded systems achieve a given task set with constrained resources. Still, they achieve real-time performance. So we program microcontrollers and related peripherals. Peripherals here refers to devices that help a microcontroller to interface with the outside world, such as a LED, a screen where we can display something, a motor, or a gyroscope, and of course, many other different kinds of sensors. We can do a lot of things using microcontrollers and together with peripherals. As for me, I work on secure deep learning on hardware. So basically, I try to make deep learning secure on embedded systems. Because in recent years, we see quite a lot of deep learning applications in robotics, such as autonomous driving. But here's the problem. Is deep learning secure for robots? What if deep learning models are vulnerable to adversarial attacks, which means deep neural networks can make wrong or even ridiculous predictions once under attack? So for example, here's a project that demonstrates how to attack an object detection system. We have several components here, and I will illustrate each component one by one. First, on the bottom right corner, we have a simulator, actually a gazebo simulator, if you are familiar with ROS, or Robot Operating System. So we have a simulated robot with a simulated camera. The simulator runs on the remote server, so it's a little bit slow here. The image captured by the simulated camera is sent to the browser. So as you can see here, we have the input and the output of the object detection model. As you can see here, the traffic sign 60 is being detected by the object detection model. So we have a bounding box here. The last component is the control panel. So actually we can navigate around using the keyboard. As I mentioned previously, this project demonstrates how to attack object detection system. As for now, the object detection systems seem to be pretty stable, right? But this is not the truth. So now I'm going to attack this object detection system by generating a patch. As you can see here, suddenly we have all different kinds of traffic signs. We have 30, 60, stop. Well, for humans, we know that these are not traffic signs. This looks like some random noises, but deep learning models recognize it as traffic signs. So this is how we attack object detection system. If we replace the simulated robot with a real robot, the same attack can be applied to real robot as well. So as you can see here, still we can generate a patch that will be recognized as traffic signs. These are some demo applications of embedded system. So now you know that we program hardware. Well, but how do we program hardware? To program hardware, of course, we need to get the hardware first. So we need a development board. If you are interested with circuit design, first we have a schematic, then we do the routing, and later after that, we send our design to manufacturers to get the PCB. Finally, we have the development board after soldering electronic components onto the PCB. Well, today I will not talk about circuit design because you come from computer application, right? So instead, I will focus on programming, how to write the code to control the hardware. First, I will introduce bare metal programming, which means we program the hardware directly without an operating system. Later after that, I will introduce Artist-Red, and I'll explain why do we need a real-time operating system. Lastly, if you find it interesting and would like to seek a future career, I prepare some resources that may be helpful. So this is the agenda of my talk. Let's move on to the first part, bare metal programming. So how do we program hardware directly? Well, we always start from lighting up a LED. So here we have a microcontroller or an Arduino, if you have already heard of it. And we have a LED. So how do we write a C program to control the LED? Well, if there's no microcontroller, you may control it using a switch or a button. So here's a battery, a resistor, and a LED. If you switch it on, the LED turns on. If you switch it off, the LED turns off. Similarly, we can control the LED using a button. So if we press the button, the LED lights on. If we release the button, the LED lights off. Pretty straightforward. Now, if we replace the switch or the button with a microcontroller, we have something like this. Basically, we connect a pin from the microcontroller with the LED. So if we set the output of the pin to be high, the LED is on. If we set the output of the pin to be low, the LED is off because both sides are connected to the ground. So we can control the LED by changing the output of the pin. Well, but how do we write a program to change it? To write the program, we read the datasheet first. So this is a datasheet for the microcontroller. It is an 8-bit AVR microcontroller. Well, the datasheet may seem intimidating at first glance. It has over 300 pages, but actually we don't really need to read through it. We can just focus on the part that we are most interested with. Say, for example, for our application, we are going to control an LED. So if I search for GPIO, we have some registers here. Well, let's move back to the slides. Maybe. Say after reading the datasheet, we know that there are some configurations in the microcontroller named as register. So for example, the port D data register is responsible for the output of the pin. So if we set port D3 to be 1, it outputs a high level and the LED is on. If we set it to be 0, it outputs a low level and the LED is off. So pretty straightforward. If we translate the configuration into assembly language, we can set the bit to be 1 or clear the bit to be 0. That turns off the LED. Well, but usually we don't write assembly language, which can be cumbersome and difficult to understand. So instead, we use SDK in C language. So it is more human readable, right? So here we write pin 3 to be high and write pin 3 to be low. So this is how we write C code to control the LED. Maybe it's more intuitive to show you some demonstrations. So here we have a simulated microcontroller. So actually, this is a web browser. So we have a simulated a microcontroller or a simulated Arduino inside the browser. So now let's add a LED. So for example, I'm going to add a LED and a resistor. And let's set up the connection between the LED and the microcontroller. Finally, I'm going to connect the other side to the pin number 3. So now we are ready to write the code to control the LED. So for example, first we can set the pin to be output because we are going to output a signal to control the LED. And we can set the output to be high. So that's it. So if I start the simulation, as you can see here, the LED is on. So this is how we write the code to control the LED. And of course, as you can imagine, if I change this to be low, the LED is off. And actually, we can even write a loop here. So if, for example, I can set the pin to be high for 1 second. Sorry, delay. So I'm going to delay for 1 second. And later after that, I'm going to write to set the pin to be low and delay for another second. So in this way, we should see a blinking LED. So it turns on for 1 second and turns off for another second. So this is how we use the SDK or the software development kit to control the LED. And as I mentioned previously, we can control the register directly. So now I'm going to replace the SDK with the register. So we can set it to be 1 so that it is output. And we can replace this line of code with another register. So this way, it outputs high. Similarly, I'm going to replace everything down below here. So replace digital write with the register. So first we set it to be 0, and later after that we set it to be, to be 1 and then 0. So if I restart the simulation, still we have a blinking LED. So this is how we write, how we use SDK and register to control the LED. A short demo. LED 101. So I have introduced how to control LED using, control the LED using a switch or a button. And we can write a C program on our laptop. Then we upload the program to the microcontroller to control the output of the pin so that we can turn on or turn off the LED. If you are interested and would like to know more about how it works in the background, I would just suggest reading this book, Computer Organization and Design. After reading this book, you can even design your own microcontroller. So this is bare metal programming without an operating system. So let's move on to the second part, from bare metal to real-time operating system. A brief introduction to RT-Thread, which is a real-time operating system, or RTOS. Well, why do we need a real-time operating system? As the project grows larger and larger, we don't really want to write everything from scratch, right? Say, for example, here's a web server running on a microcontroller, and we can receive the user input from the website and do the image recognition on the microcontroller. Well, actually, it's a live demo. So, let's say, for example, this is the website. This website runs on the microcontroller. And if we write a digital number here, it will be recognized as 0. Maybe I can clear it and write another one. So it is recognized as 0. And actually, the number written on the website is sent to the microcontroller. So let's set up the connection. So this is a microcontroller, RT-Thread. So maybe let's zoom in a little bit. So if I send the number on the browser, it is sent to the microcontroller. So as you can see here, we have the same number here. And there is a deep neural network to do the prediction. So this is a demo application. For this project, if you write from scratch, you need to implement the IP stack to set up the network connection, because if there is no IP address, how do you set up a server? And you need to implement a file system so that you can read the website from a SD card. And you need a debugging interface, the terminal I just showed to you. Sometimes, if we do not have access to the serial port, we need a telnet server to connect to the board remotely. So let's take a look at the overview of this project. Do you really want to write all of this from scratch? Well, at least I don't. Besides, in the future, if you would like to use a new microcontroller that has a better performance, unfortunately, you may need to re-implement all the drivers once again, because the same code cannot be applied directly to another hardware. Well, rewriting everything once again is a real nightmare. So therefore, we need a real-time operating system to do this for us. So using a real-time operating system such as RT-Thread, there is a hardware abstraction layer, which means the same code runs on different microcontrollers. So you write the code once, and it works for over 100 microcontrollers supported by RT-Thread. Well, actually, you can find the full list here. So if I open the this is the official website of RT-Thread, and here is a list of all the chips and boards supported by RT-Thread, and the list is still growing fast. So actually, in addition, the operating system provides the file system, the networking, the POSIX layer, which I will introduce later, the shell, and etc. for you, so that you can focus on your application, and the operating system manages the rest for you. So life is much easier with the help of an operating system. And of course, there are many other choices. FreeRTOS, Zephyr, NuttX, they all provide support for different hardware, the file system, networking, and software packages. Well, today, of course, I will use RT-Thread as an example. So still the same project here. I will illustrate each component used in this project: the hardware abstraction layer, the file system, networking, the POSIX layer, and some software packages. So let's move on to the first one, the hardware abstraction layer. Well, actually, I've already introduced this before. With the hardware abstraction layer, the same code runs on different hardware because it provides abstraction for pin device, UART, analog to digital converter, digital to analog converter, CAN bus, I2C bus, SPI bus, and etc. You can find the documentation online. So here's the documentation, and you can find all different kinds of devices here. So this is hardware abstraction layer. As for networking, we can connect to the network using Ethernet, Wi-Fi, GPRS, and etc. RT-Thread provides a socket abstraction layer that supports BSD socket interface. If you are familiar with Linux, you should feel at home while using RT-Thread. Here are several commands available for networking. Well, maybe it's more intuitive to show you in the terminal. So here we have RT-Thread up and running. Maybe let's zoom in a little bit. List all the devices available here. Use tab, always use tab to autocomplete. So we, as you can see here, we have several network interfaces, and maybe I can do a Wi-Fi scan. So, oh, it's better. Zoom out. We can see there are several wireless networks available here. And if I do a Wi-Fi status, this all runs on the microcontroller, by the way. So currently I'm connected to my router, of course. So since I'm connected, let's see my IP address. So this is my IP address. If you still remember, this is the IP address for the website. So the website is hosted on the microcontroller. And we can see the DNS server. And since we are connected to the network, let's see if we can ping google.com. Oh yeah, yeah, indeed. So we do have internet access. And as I said, sometimes if we do not have access to the serial port, we can connect to the microcontroller remotely. So here, actually this one is a Ubuntu 2004. So now I'm going to connect to the microcontroller using a telnet client. So I'm going to use telnet and the IP address of the microcontroller. Oh, sorry, telnet. So now we have the same terminal here. We can list all the devices and we can see the IP address using ifconfig. So this is, let's exit, create a connection. So this is networking, RT-thread networking. Now let's take a look at the file system. We can read files from SD card, SPI flash, NAND flash, and even network card. RT-thread supports all different kinds of file systems here. And similarly, here are several commands available in the terminal. Well, if you are familiar with Linux, you should see something familiar here. So let's move on to the terminal. Say, for example, this is RT-thread. So I can list all the files in my SD card. So using ls. So we have several files and directories. And I can change directory using cd. Now we are in a new directory, and these are all the files in this directory. And we can use pwd, which is the same as Linux. We can see the current working directory, and we can move back. And maybe we can create a new file. So I can echo hello to the terminal. And maybe I can echo hello to a file named hello.txt. Yeah, so now we have a new file here, hello.txt. And we can use cat to see what's inside the file. So we have hello inside. And maybe I could show you the website. So we have the index.html here. So I can see all the contents of the website. Oh yeah, so this is a web file system. Maybe I can even make a directory using make directory. So as I said, if you are familiar with Linux, you should feel at home. So everything is virtually the same. The reason we can use so many Linux commands and Linux software in RT-thread is because RT-thread provides the POSIX layer. POSIX represents the portable operating system. Actually, it's a standard enforced by IEEE. So the purpose of POSIX was to improve portability. When your source code follows the standard, you can compile and run the code on both Linux and RT-thread, and of course, many other different operating systems. I'm not going to read through it. If you are interested, you can always find the documentation online. So here we have, we have the documentation for the POSIX interface. In one sentence, with POSIX layer, the same code runs on different operating systems. Well, maybe I can show you more Linux applications running on RT-thread. So we have the software package center. So in the software package center, we have nearly 400 packages. Some come from Linux. Well, maybe I can show you on the website. This is RT-thread software package center. We have a lot of packages here. IoT, peripherals, system, programming language, tools, miscellaneous, multimedia, security, and AI. Maybe I can show you how to add a package into your project. So this is RT-thread Studio, where we develop a project. So actually, it can be downloaded from here. So we have RT-thread Studio here, which is IDE or Integrated Development Environment. So you can download RT-thread Studio here. it has already been downloaded here. So now I'm going to create a new project, a new RT-thread project. Say the name should be Hello RTT. And here I'm going to use a simulator. So I'm not going to use the real hardware. I would like to show you how to simulate RT-thread in a simulator. So I'm going to use QEMU simulator. Just wait a while. So the project is creating. Basically, it copies all the source code into your workspace. It may take a while while it is copying the file. Maybe we can see some packages here. For the programming language, we have JavaScript, which is similar to JavaScript, and we have Lua, MicroPython, PikaScript, which is a lightweight Python. Oh yeah, it's done. So we have our project here, and I can just compile it. It should give no error because it is a new project. Let's wait for a while, and it compiles. Oh yeah, it compiles. So we can start the simulator. So this is the same board I'm going to use. So now we have a RT-thread running inside a simulator, right? So the same operating system here. Now I would like to add some packages into our operating system. Say for example, or let's stop. Say for example, if you double click RT-thread settings here, we have the software package center here, and we can enable different components from here. So now let's add some packages. Say I would like to add Lua and MicroPython into our project. As for the MicroPython, we can choose the version. So maybe let's use the latest version. So if I press Ctrl and S to save the configuration, as you can see here, the RT-thread ID automatically clones the repo or the project into our workspace. So it is cloning Lua and MicroPython, and it is done. Oh, it's still, yeah, it's done. So we can see now we have Lua and MicroPython being added to our project. Now let's compile this project again. This may take a while because now we are compiling both Lua and MicroPython. So while it is compiling, maybe let's see if maybe I can show you more applications on RT-thread. So for example, let's see what we have here. We have a running locomotive. So this is and we have the same application on Linux. So this is Ubuntu. So the same program runs on both Linux and RT-thread. And oh yeah, this is Linux. Let's see if we have anything else. We have say hello. We can say hello, and we have the same program on Linux. So this one is Linux. So the same program runs on both Linux and RT-thread. And let's see. Oh, maybe. Oh yeah, we have a donut, and we can even play animation in the terminal. Let's go back to see. Oh, it is still compiling Lua. And maybe I can reset the board so you can see the starting process. So now I just restarted the operating system. So after restarting the operating system, it automatically connects to the wireless network and retrieves the IP address. Oh yeah, so this is a booting process. Oh yeah, it compiles. So now let's start the simulator again. In this time, we have Lua and MicroPython in our project. So oh yeah, the simulator should be STM discovery. Yeah, so we have the simulator, and now we can run Lua. If you are familiar with Lua, you can print let's say hello. This is Lua. Oh, sorry, there's a syntax error. Anyway, and similarly, we can run Python here. So this is the Python interpreter running on RT-thread. Similarly, oh, sorry, this. Similarly, we can print hello. There's no syntax error. But of course, this is MicroPython. So this is how we add software packages into our project, and I've demonstrated how to simulate RT-thread in a simulator. This is almost the end of my talk. If you find embedded programming interesting and would like to become an embedded system developer in the future, so here's a summary. First, for bare metal programming, there are quite a lot of popular microcontrollers around the world. The Arduino platform, the STM32 microcontroller, which has been used in my demo application. We also have ESP32 microcontroller that comes with Wi-Fi and Bluetooth built in. And the last one, the RISC-V architecture that is energy efficient. For real-time operating system, we have quite a lot of choices: FreeRTOS, RT-Thread, Zephyr, NotX, just to name a few that are open source. For some project, we can even use embedded Linux so that we can take advantage of existing Linux software. If you are concerned with safety, you may be interested with a Rust programming language. Sometimes writing C code to manage memory can be unsafe, while the Rust programming language provides memory safety at compile time. Besides, when it comes to safety, we have cryptography on embedded systems as well. And the last one, if you work on the project that deals with high-speed data processing and transfer, you may use FPGA. Now it's quite common to have both FPGA and microcontrollers in the same system for hardware acceleration. Well, of course, we still have many interesting topics to explore, but we have quite limited time here. So this is the end of my presentation. Hope it may be useful for you. And if you have any questions, feel free to post it in the chat box. Yeah, thank you. This is the end of my presentation.